All right, let's dive into a question that gets to the very heart of what's real in physics. Our textbooks tell us that the only way to influence a particle is to actually hit it with a force. But what if the textbooks are, well, not wrong, but missing a huge part of the story?
Just imagine an electron flying through what is truly empty space. The puzzle we're tackling today is this. How in the world do you affect that particle when it's in a region with absolutely zero electric or magnetic forces pushing or pulling on it? I mean, that sounds impossible, right? It's like trying to steer a ship with no wind, no rudder, and no engine. It is the very definition of action at a distance. And for over a century, the consensus was pretty clear. You just couldn't. It was impossible. But then, in the 1950s, a totally mind-bending experiment was proposed that proved they were fundamentally wrong. And this discovery didn't just win a Nobel Prize. It split the physics community and forced them to question the very nature of reality itself. Now, the tool that would eventually unlock this whole modern quantum mystery, well, it wasn't new at all. It was actually invented centuries earlier to solve one of the oldest, hardest problems in all of classical physics. And what's so fascinating here is the stark contrast. On one side, you've got the two-body problem. Think Earth orbiting the sun. Newton solved that one, no problem. The forces are predictable, they're elegant. But then you add just one more body, say the moon, and you get the infamous three-body problem. And suddenly, everything just descends into this chaotic, unpredictable mess of interacting forces. For 100 years after Newton, the greatest minds were totally stumped. Then, in the 1770s, this guy, Joseph Louis Lagrange, comes along. Now, he didn't solve it. In fact, we later found out it's literally unsolvable. But in the process of trying, he invented a brilliant new mathematical approach that would change everything. Lagrange's genius was to just stop thinking about forces, those messy vectors with direction, and instead imagine a potential landscape. Think of it like this. A massive star creates a kind of gravity well in the fabric of space. The value at each point on this map is the gravitational potential. It's a scalar, which just means it's a number, like altitude on a map. No direction, just a value. And this is where his idea just clicks. To find the force on an object, you just place it on this landscape and see which way it would roll. The steepest downhill path tells you both the direction and the strength of the force. And just like that, a totally chaotic vector problem becomes a much, much simpler scalar one. So this new tool was incredibly powerful, but it raised this deep philosophical question that would just linger for over a century. Was this potential landscape just a clever mathematical trick, or was it something physically real? Naturally, this idea got adapted for other forces pretty quickly. The electric potential, which we call phi, was a lot like gravity, but you had attractive wells for opposite charges and repulsive hills for like charges. Magnetism, though, that was trickier. Its field lines are continuous loops, so there's no clear downhill. It actually took a brilliant undergraduate, William Thomson, who you probably know as Lord Kelvin, to invent a whole new mathematical tool called the curl to describe this swirling magnetic potential, which he called A. Okay, but here is the absolute crucial point. This is the reason physicists dismissed potentials as being physically real for so long. The actual absolute value of the potential, it doesn't matter at all. You can raise or lower the entire landscape by any amount you want. Add 10, 100, a million, and the slope at any given point stays exactly the same. The resulting force doesn't change one bit. So the conclusion seemed, well, obvious, right? If you can change its value however you want without any physical consequence, then the potential can't be a real physical thing. For over 150 years, that was it. Case closed. Potentials were just a convenient mathematical fiction. But that long-held dogma was about to get completely shattered. In the 1950s, two physicists, David Bohm and his student Yakir Aharonov, dared to ask a really radical question. What if everybody was wrong? And David Bohm, he was the very definition of an outsider. He was actually recruited for the Manhattan Project by his own advisor, J. Robert Oppenheimer, but he was quickly banned as a security risk for some past communist sympathies. He was questioned by Congress, lost his professorship at Princeton, and was basically exiled from the American physics community. He eventually landed in England. So while he was in exile, Bohm and Aharonov noticed something profound that pretty much everyone else had overlooked. When you look at the Schrödinger equation, the fundamental equation of all of quantum mechanics, the math in there doesn't use electric and magnetic fields. It directly uses the potentials, A and phi. And they wondered, what if the equation was telling us something
literally about how reality works. So they came up with this brilliant experiment. First, you split a beam of electrons so it passes on either side of a solenoid. That's just a long shielded coil of wire. Now, critically, the magnetic field is trapped inside the solenoid. So if potentials aren't real, turning on the current shouldn't do anything to the electrons outside. The interference pattern they make should stay exactly the same. But if potentials are real, the magnetic potential A that leaks outside the shield should shift the phase of the electron waves, changing the pattern, even with zero force acting on them. Their paper in 1959 was met with, let's just say, a lot of skepticism. The great Niels Bohr himself found it impossible to accept. For decades, experimentalists tried and failed to get a clean result, always plagued by tiny stray magnetic fields that critics could point to. That is, until 1986. A team in Japan, led by Akira Tanomura, they finally cracked it. They used this tiny, perfectly shielded donut-shaped magnet to create a region with absolutely zero magnetic field, but a definite magnetic potential. They ran the experiment, and the interference pattern, it shifted. Aharonov-Bohm were right all along. The effect was undeniably real. But proving it was real didn't end the debate at all. Nope. It just kicked off a new, even deeper one. What on earth does this actually mean for the nature of reality? Physicists basically split into two main camps. Camp 1, which included people like the great Richard Feynman, argued that this proves it. Potentials are real, physical things that locally affect particles. Camp 2 argued, no, fields are still what's real, but this experiment reveals they can act non-locally, that is, influencing things from a distance. And oddly enough, Aharonov himself eventually moved over to this second camp. Richard Feynman's reaction just perfectly captures how mind-bending this all was. He wrote, A is as real as B, realer, whatever that means. I mean, that just brilliantly illustrates the profound confusion and the wonder that this result sparked in even the greatest minds. So where does that leave us today? Well, the debate still rages. And this isn't just old news. As recently as 2022, researchers actually demonstrated a gravitational version of this effect, which suggests this principle goes way beyond just electromagnetism. The old textbooks aren't wrong exactly, but they are clearly deeply incomplete. Our understanding is still evolving right now. And that leaves us with this final, really provocative question that physicists are still grappling with. What's more fundamental to reality? Is it the force field that we can physically measure and feel? Or is it the abstract mathematical potential that seems to be pulling all the quantum strings from behind the curtain?